Look, I had to get up too. I realize all you guys probably slept till noon, but I had to get up also this morning. Noon. Oh my goodness. I think the most I sleep is till 8 o'clock. That's it. Yeah. Okay, so in keeping with this, we've got probability distributions, we've got binomial distributions, we had a little bit of skewing on your graphs. This is a good example of a probability distribution. See this right here? These are your probabilities. Now, what that first part of this homework asked you, and I'll erase all this so we can see it, was to identify where you think your probabilities would be. So, again, if you make an example to yourself, like 90%, I predict 90% of the class will pass the next test, you have more people passing. It's got to be higher, and it's got to be the taller bars and the larger numbers. So this guy had to have a probability greater than 0.5. It's skewed to the tail, so it's skewed left. My higher numbers sit right there. This guy was symmetric, so it had a 0.5. This guy was skewed to the right, so your probabilities are stronger here. Which is, if I said, on my next test, I think the probability of passing is about 30%. Do I expect a lot to pass or less to pass? Do I expect, if I say the probability of passing this next test is 30%, what do you automatically say to yourself? Oh crap, I'm not going to pass, right? If the probability of passing is 30%. So do I expect more to pass or less to pass? Less to pass. So I'm not going to get my bigger bars here, I'm going to get my bigger bars there. And the smaller numbers. This one you just had to place your N. And this is a good clue here because this is your a value of X, the value of N, basically. So look for a 4. Here's your 4. Look for an 8. There's your 8. And look for a 12. There's your 12. You know, use your book, guys, to go over this with me so that it starts to come back to you. I wanted this completed before we left, but it didn't work out that way. We had 3 little formulas to find the mean, to find if we're only given an N, and we're given a standard deviation, if we're given an N and a P, we can't find our standard deviation unless we have an L1 and an L2, and you stick it in your L1 and L2. But if they give us an N and a P, we can find our Q, we can find your mean, we can find your variance, and then from your variance, we can find your standard deviation. Okay, so we have those little formulas. You have to know those little formulas. Because otherwise, how would you find the mean and the standard deviation of something that you don't have a table to stick your L1 and your L2 in, right? I can use this formula on a table as well. I don't have to put my L1 and L2 in there. I can cut to the chase. This is good for your binomials. You tell me, are you remembering this? Is it what you have on your paper? I need you to have your book, and I need you to have your work that you did, and compare it. Good? We're on target. So we can use these nice little formulas to find the mean, the variance, the standard deviation. Okay? Right? And you had, this one just wanted to know, were these a binomial distribution or not? Again, we have 4 criteria that it has to meet. The easiest way to determine it is start laying out your pieces. If you get stuck and you don't have one of those, then whoop, you don't have a binomial distribution. So a survey found that 49% of households own a dedicated game console. 8 U.S. households, there's your N, are selected at random. The random variable represents the households that own the dedicated game. this part tells you it goes from 0 to 8. That's good. That meets this criteria. My variable is from 0 to the number, the highest number. I've got n. I've got a fixed number of trials. There's my fixed number of trials. I have a probability of two things. Either they say yes, they have a dedicated game console, or they say no. Two choices. Success, failure. I get two choices, success and failure. The important part is, does this probability change from trial to trial? Say no, no. This stays fixed. Each trial is independent of the other one. What would make this probability change? How? How would I change the numbers? Oh, okay, but give me a good example. How would I change a probability?
Change how many times you did it.
Not how many times I did it. I pick a household and I don't replace them technically. But this is Richard, not replacement, right? These are all independent. Each time I do this, it's the same probability. I expect 49% of the households to own a console game. If I say I surveyed 49 out of 100, I picked one and I put it to the side. Now my probability will change. Not that that's feasible to do, but that's how my probability would change. Like this one. Watch this one. You draw 5 cards, one at a time from a standard deck. You do not replace the card. The random variable represents the number of cards that are hearts. How many hearts in your deck? 13. So my random variable is good. And it is two choices. I'm either going to be a heart or I'm going to not be a heart, right? So far, so good. So what is the probability of a heart?
13 out of 52.
You don't replace it independently?
It's dependent. Because now, watch, I picked up a heart. I'm holding it. I'm not putting it back.
Now,
Right, it changes this. So how many hearts are left? 12 out of how many cards? Ah, so your probability changed. So it was dependent on what I first told. How could I make this a binomial distribution? How could I make this so that the probability doesn't change? Replace my card. If I replace my card, is my probability always going to be 13 out of 52? And then I have a binomial situation.
has to be independent.
It has to be independent. If your probabilities change, then it's not going to be a binomial. Binomial says it has to be the two choices. Probabilities are fixed, right, and it's independent. Coming back to you, I feel it. Okay. To his left. All right, 39%. Again, pull out your pieces. 39% of all U.S. adults think that the government should help fight child obesity. Either they say yes or they say no. Two choices. We randomly select 6 adults. There's your N. You want to find a probability that it is exactly 2, at least 4, less than 3. So we built a table. We said N is 6, probability of success, 1 minus that, probability of failure, and here's my random variable x. It could be 0, 1, 2, 3, 4, 5, 6. We did your binomial PBS. Try it in your calculator, guys. Hello, Mrs. Moore. Hello, Mrs. Moore. Good, how are you? Yes, I do. Yes. Hey, come on, talk to him and see what he can do. Okay, hold on. I'm sure he'll be excited. Hold on. Coach. The head coach from Maine is here. He doesn't look excited, I don't know why. Okay, remember we did this on your calculator. Binomial PBS. N, P, Q. In order. In alphabetical order. Okay. How many times I can do this? 6. Probability of success. Oh, no, this is X. Sorry. X. And then start with the 0. Then we replace it to 1. Then we replace it to 2. Okay. Do you remember doing that part?
Do that in the calculator again? You gotta copy and paste it and then change the number.
You just have to do down to the, yeah, and then you can just keep changing that. It's second pairs. I think it's either letter A or O. I can't remember. A? A. Now, you don't want the CDF. CDF is cumulative. You want the PDF.
It's trials.
No, second row.
Second pairs. Go down to binomial PDF. Guys, please try this. Now, we also did the C with this. I have 6 things, 0 at a time. Measure my success first. My failures next. Okay? We could do it that way and change it each time. Got it? See data, I knew it would come back to you. Okay, once you lay out your table, this is your probability. Once you lay out your table, all your other information comes from your table. What is the probability of exactly 2? I go to my table, and there it is. My probability of at least 4. At least 4, think money in your pocket. 4 or more. 4 or more. I add up my probabilities. Probability that it is less than 3. Less than 3, can I count 3? No. So I come here and I say less than 3 and I add those up. Add up your probabilities. Okay, once you get your table, you can do anything you want off your table. Makes life a little easier.
Can you do the PDF or that statement here? What is that number that came to? I mean, it says.
I don't know what you mean.
One time, but what is it?
This is your first entry of the table. I just rounded it to 3 decimals. Then you're going to change this to a 1. That's the second table. Then this to a 2. Good?
The thing with calculator.
The calculator is so easy.
That's the whole thing.
Yeah,
As long as you know how to read. Like,
yeah, as long as you understand this part.
yeah.
Like I said, did I try it with your group in Algebra 2? Did I do this?
The part that gets me confused is like the first time you do it, you have to put the 0 in,
Yeah, put the
and
zero.
then you have to go back and switch the whole thing for 1 and switch the whole thing for 2.
Yeah, that's it.
Yep.
That's it. Second enter.
Yep.
Just do second enter. 1, 2, 3, and do them all. If you do this, you have to change it here, here, and here.
And in the app, you just have to keep changing it.
That's all you have to change is one spot, right here. I find this is a nice step on your calculator. So much faster. And like I said, I don't know if I told you, I tried it with my Algebra 2s one time a few years back when I had Algebra 2s. And I did my Algebra 2s this, but I don't think they had enough understanding of what a probability distribution was, what a binomial distribution was. I think you develop a deeper understanding, so it makes more sense when we do the table. They didn't really catch that. Yet, my kids that took the algebra regents of January or June use this to do that part, those questions, and that's fine. Okay, again, pull out your pieces. 56%. You randomly select 8 men. You find the probability who do not look forward to going clothes shopping for themselves. Same, it has to match this. That's what you're looking for. So again, you have your table from 0 to 8. I caution you guys, be careful on your calculator. If it says this, your probability can never be greater than 1.
You have to multiply to the negative fifth, right?
You got to move your decimal 5 places to the left. This is a scientific notation number. If you move it 5 places, you add 4 zeros. And you need to go out to at least a significant digit. You can't make it be 0. Even though we go out 3 decimals, you can't make it be 0 because 0 says impossible to happen. Yeah. Well, you go by this, 8. So out of the 8 that I selected, 0 could say that they do not look forward to going. 1 could say, 2 could say.
Last one was 6.
Mm-hmm. Mm-hmm. 8 of them could say they do not look forward to go shopping. What is the possible choices of your random variable? This is your random variable x. Okay?
This one.
Yes. Yes. Then from this we can pull out your exactly 5. We can pull out your more than 5, does not include 5. We can put your at most 5. Here's your more than 5. At most 5, if you think money in your pocket, says 5 or less. That's this. So you could use this condition. What is that condition called? Complement. Good. This is your complement condition. There's no other pieces that it's missing. And the sum has to add up to what? 1. Okay? Or you could just add these pieces up. Whichever you prefer to do. Good? I'm not used to this room being so quiet. Okay. For this, we had to build this. We had to graph this. This is the same as your relative frequency graph. So, again, pull out your pieces. 67%, there's your P. Q is 1 minus that. You randomly select 7 adults, so your table is 0 through 7. You find your probabilities, and we graph it. You need to label, title, make your bars close together. Now, where is the skew on that graph? To the left. Now, I want you to think this out a second. Why is it skewed left? Because, okay, let's think this out. You said the probability is what? Less than 0.5? So, are less people picking this, or are more people picking this? More are saying yes. So what do you think your probability has to be? Greater than 0.5. Think something real simple, like the probability of me giving the next test is 90%. Will more people pass, or will less people pass? More. My bars have to be higher on this side. But it's a backwards way to say this, so I'm skewed left. The higher numbers are on the right-hand side, but I have to follow the tail. So I'm technically skewed left, but my probability was greater than 5. And let me check. Oh yes, my probability was 0.67. I expect more people to say yes with the higher probability. If I do a survey, and I find that the probability of the seniors in the school to go to college is 75%, do I get more kids going to college or less kids going to college? More kids going to college. So my bars are higher on the right-hand side by the higher numbers, but I'm skewed to the left. Make sense? Make sense out of your numbers. Okay, again, you had to do another graph. 38%. Here's my P. You randomly select 10. There's my N. There's my random variable at work. For the binomial PDF in your calc, find all those pieces and give me a graph. Now, where would you say the skew is? To the right. It's slightly to the right. So my higher numbers are falling more here. Less people are saying this. So the chances, my probabilities are usually smaller. My probability should be less than half. Half would put me smack in the middle, would give me a symmetrical graph. If my chances of less people saying yes, then my probability is smaller. And let's check. Yeah, your probability is smaller. Yes. No, the Q, you need to,
No, I get it. I just don't know what you do.
well, not in your binomial PDF, but if you use the C, you have to use the Q. That's when you use the Q. The binomial PDF does. But if you use the C, the Bernoulli's, you have to use this one. Do you guys have this down? Is it coming back? And then the last part of it was using your formulas. And you should realize you're going to have to use a formula here because you can't make a table for, well, you can, but on this one's not so bad. It's only 4. But if it said like 40, you definitely wouldn't want to make a table. I could make a table for this one from 0 to 4. I could use my binomial PDF, and then I could do my L1, L2. I could do L1, L2 if I wanted to. But I have a nice way to do it. I have my 69%, my P, 1 minus that, my Q, N is my 4, and now I have my formulas that will do this for me. And the square root of that is here. N times P, N times P times Q, and then the square root of that. And I don't have to make a table. Normally we use this especially if you're doing this 400 times. You certainly don't want to make a table for 400 things and put that in your L1, L2. Can everybody use those formulas? Oh boy, I hope tonight to get a better night's sleep. And last one, 31%. Again, we can make a table from 0 to 6 if you want to, do L1, L2. Or since we only want the mean standard deviation, you use your little formulas. N times P, N times P times Q, and then take the square root for your standard deviation. Now, let's just talk about what this means when we do this. Remember, your N times P is your mean. It's also your expected value. Is what you expect to happen. Now, just because it says a decimal, 1.86 adults, doesn't mean I'm going to get a 1.86 part of an adult. But that's on the average. I expect their life, that they think that life will be existing on Mars at some point in our future, whenever. I expect 1.86 out of the 6 that I surveyed. So probably about 2 people I expect to say yes. We'll think that that's true. On the average. Remember, statistically, people have 2.5 children. They have 1.3 animals. That's the average. Your average is always 1 more decimal place than your regular data is. Good? All right. Now, I realize this was a lot to digest just